Hi, and welcome back to my Physics Online video lecture series. Today's video, we're going to be doing the wave on a string from a simple algebra-based physics perspective. So, wave on a string, specifically a traveling wave on a string, basically what you have is your string which is under equilibrium conditions, maybe like this. It has some particular total length from one end to the other. It has some particular mass. And these two parameters combined give us what's called the linear density of the string. So that is mass per unit length for the string. And then the other thing about it is under these equilibrium conditions, it also, for any given point on the string, has some amount of tension present. So there's some tension force present in this string. Now, the speed at which a wave will propagate along this string, so we'll call that propagation speed, v. In general, v is given by the wavelength times the frequency, or it's given by the wavelength divided by the period. So in general, this is true whether we're talking mechanical waves, whether we're talking transverse, whether we're talking longitudinal, mechanical, electromagnetic, whatever. So in general, this equation is true. Oops, not doing a very good job of circling it though. And where this equation comes from is basically just that the speed in general, v, we define as how far something travels divided by the amount of time that it takes to travel that distance. And so if we consider one wave moving by one wavelength, delta x would become lambda. And by definition, if this is true, then delta t becomes the period. And since frequency and period are reciprocals of each other, this middle equation also follows. For a wave on a string, we have an additional equation that can be used to determine the speed. So wave on a string, we can also note that v is given by the square root of the tension in the string, Ft, divided by the linear density, the mass per unit length. And so if you have a string that has a definite length, maybe it's fixed on, maybe you've like cut it off of a spool of string, so it has a particular length to it, then you can mass that little length of string and measure its length, and this equation becomes Ft times L over m, all under a square root. Okay, so that's how you get the speed of a wave on a string. Let's do a very quick example of this. So, quick example. Let's say that you have a string of known parameters. Specifically, the length is known, the mass is known, and the equilibrium tension is known. And so we want to determine the speed of propagation, and then while we're at it, we want to know what frequency will result in a wavelength of 125 centimeters. Okay, so speed of propagation, we can use v is equal to square root of the force of tension divided by the linear density. In this case, we've been given the length and the mass, so we would actually want to use the other form of the equation, force of tension times the length of the string divided by the mass of the string. Okay, so this ends up looking like the square root of, and then force of tension is 24 newtons is given, as is the length. This is 125 centimeters, but we need to convert it over to meters if we want to get a speed in meters per second. So that's 1 meter per 100 centimeters. This is a 1.0, by the way, or 1.00 if you prefer. The mass is 6.25 grams, so 6.25 grams times, again, 1.0 kilogram per 1,000 grams. And everything here is actually under this square root. So we would plug this into our calculator to get. So everything inside the square root would come to 4,800. And so then you take the square root of that, you get 69.2820. So we could say that this is a speed of approximately, let's say, 69 meters per second using two significant figures. And then for the second part, what frequency results in this wavelength? So again, V is lambda f, and that means that f is V over lambda. So now we have to divide this speed, and again, I've got it in my calculator, 69.2820, and we divide it by the wavelength, which we're going to want to actually convert over into meters. So again, doing the same unit conversion. So let's say 69.28 to whatever meters per second divided by 1.25 meters. And so if I divide this by 1.25, I get 55.425. So again, this means that the frequency is about 55 hertz, or 55.4 hertz. We'll break the significant figures rule and include a decimal here. All right, so that's our example. So what does a wave traveling on a string actually look like? Well, this in some sense is kind of a rehash of what I've already said about traveling waves in general. Wave on a string is a type of one-dimensional wave. So if my string at equilibrium is represented by this dashed line, then at some particular moment in time, this wave will just look like a sine wave about this equilibrium point. And so this right here might represent my wave at a given moment in time. And so this height right here would represent the maximum displacement, or the amplitude, in other words. This right here would represent the maximum displacement in the opposite direction. Switch colors because of it'll get cluttered otherwise. This distance from here at the peak to here at the next peak would represent one wavelength lambda. And I could describe this entire wave if I decide to put a little axis to it. So let's put a little x and y axis on here. This right here would represent the y-axis. This dashed line right here actually could represent also the x-axis. And so this sine wave is described as y is equal to y max times the sine of the wave number kW times x minus the angular frequency omega naught times time, and there may be some additional phase offset. I could rewrite this part of the equation in terms of wavelength and period instead, and so this would become the amplitude y max times the sine of, and basically I could just pull a 2 pi out, and what's left inside is x over lambda minus time over period, and then that all plus your initial phase. Okay, so that describes the wave in space and time. There's actually another thing we can do here, which is if we recall again that v is equal to lambda over t, and I just made use of kW wave number, that is 2 pi over lambda, and the angular frequency omega naught is equal to 2 pi divided by the period. So this right here is actually given by the angular frequency omega naught divided by the wave number kW. And so I could come back in here and basically divide a kW out of everything. So if I divide this term and this term both by kW, so divide out a wave number, then I can rewrite this in terms of the speed. So y max times the sine of, and essentially I would have, let's put it like this, kW times x minus vt plus phase. So that's another way of writing that same wave equation. Okay. There's maybe one other thing to really talk about, two other things to really talk about here, just for completeness sake. One of them is energy. So energy, and energy, just, for a spring, you would write something like U, or energy or whatever, U max is equal to 1/2 K spring times the maximum displacement, x max squared, or delta x max squared. Okay, for this string we can do something similar, but what we have to do is recall that omega naught squared for the spring is equal to the essentially ratio of spring constant Ks divided by mass m. And so that means that Ks is equal to omega naught squared times m. And so we can use that to figure out the maximum energy of the wave, the maximum potential energy. And the nice thing about figuring out the maximum potential energy is at any point on the wave, some of it, the wave may be moving or it may momentarily be stationary. You've got kinetic and you've got potential energy. And so this maximum is simply given by the mass of the string times the frequency squared times the maximum displacement. Now usually we do this is the second thing, in terms of per unit wavelength. And to get that, what we basically do is divide by the length and multiply by one wavelength, which gives us this final